Hi everyone. In the series of perturbation theory, today we are going to discuss the first order correction to wave function. So, what does it mean the first order correction to wave function? Here, first order correction to wave function means we need to find actually psi n of psi n to the power of 1. We need to find. So, this is the first order correction, isn't it? Our target is to find psi n power 1. So, in the earlier classes, we have seen the expansion and we have seen zeroth, first, and second order perturbation equations. Now, and also we have seen the first order correction to energy. In this class, we are going to discuss about the first order correction to wave function. Wave function, that is first order correction to wave function psi n power 1. So, to find this correction to wave function, we need to understand what is Rayleigh-Ritz method, and also we need to know what is completeness rule. So, according to Rayleigh-Ritz, here every perturbed wave function is a linear combination of unperturbed state, except that state which we are finding. If you take example of this four states, here we are having phi 1, phi 2, phi 3, phi 4. These are what? These are unperturbed state, undisturbed state. If the system is before disturbing the system, the states functions are the states are like this. That is phi 1, phi 2, phi 3, phi 4. And the corresponding perturbed states after the disturbance happened, after the perturbation of that system, there will be perturbed states, that is psi 1 of 1, psi 2 of 1, psi 3 of psi 3 to the power of 1, and psi 4 power 1. These are what? These are perturbed states. So Rayleigh did tried to explain about these states. Like he considered that unperturbed states are phi 1, phi 2, phi 3, and phi 4, and perturbed states are psi 1 of 1, psi 2 of 2, psi 2 of 1, psi 3 of power 1, and psi 4 power 1. So what he said? So every perturbed wave function is a linear combination of unperturbed state. So what he is trying to say is that here, if you observe, what are the perturbed states here? Let us say psi 1 of 1 is a perturbed state. If I say psi 1 of 1 is a perturbed state, that is psi 1 of 1 is perturbed states. If I say, what he is trying to say, every perturbed wave function, this is the perturbed wave function, is a linear combination of unperturbed states. So it is telling that it is a linear combination of unperturbed states. So C1 is any coefficient, let us say. So C1 is what? C1 is any coefficient, if I say, that is C1 phi 1, because linear combination of unperturbed states. This phi 1 is an unperturbed state. C2 phi 2, C3 phi 3, and C4 phi 4. So this is what? This is the linear combination of unperturbed states, which is equals to every perturbed wave function. This is a perturbed wave function which is equals to linear combination of unperturbed state. So what he is trying to say, he's saying that except that state which we are finding. If you are finding that psi 1 of 1, so psi 1 of 1 you are finding, then we need to take out this C1 phi 1. So we need to neglect this C1 phi 1. The linear combination of C2 phi 2, C3 phi 3, C4 phi 4 we have to include. Okay, except that state which we are finding. As we are finding the first state, we need not to be included this term in the expansion. So here, if you want to find a C1 of 1, we need to take out this term. If you want to find C2 of 1, you need to take out this term. I hope you understood. Like this, we have to do the Rayleigh-Ritz method. So if you see the example here, C1 of 1 if you want to find, then we need to cancel this term, and all other terms must be in a linear combination. Where phi is what? Phi is an unperturbed state, and psi is what? Psi is a perturbed state. So therefore we can write the function psi n power 1 is equals to summation over m cm phi m. That is cm is any constant here. phi m is an unperturbed state. So here m and n will not be equals to uh, will not be equal. Okay, if you want to find psi 1 psi 1 of 1, this must be from 2. Okay, from 2, so it is not equals to n. Okay, m is not equals to n and n is not equals to m. We need to understand that. So this is the Rayleigh-Ridge method. And another rule we have to understand, this completeness rule. That is completeness rule in finding this psi n power 1, as our target is psi n power 1, that is first order correction to wave function. We can write psi n power 1 is equals to how? That is identity operator into psi n power 1. Identity operator into psi n power 1. This is, let us consider this is equation number 2. So by completeness rule, we can write I cap is equals to, that is identity operator is equals to summation over m, that is sec phi m into bra phi m. So this is how we can write. So that identity operator is equals to summation over m sec phi m into bra phi m, and we need to substitute this term, this I value, in equation 2. If you substitute that value, you will get this equation, that is psi n power 1 is equals to summation over m phi m get phi m into inner product of phi m into psi n power 1. So that is psi n power 1 is equals to n not equals to n summation over n not equals to n, and we have interchanged the terms, like that is inner product of phi m into set, that is inner product of phi m psi n power 1 and set phi m, that is equation 3. Let us consider. Now what is our target? Our target is to find the first order correction to wave function, right? So we need to write the first order perturbation equation first. So we are writing the first order perturbation equation. This is the first order perturbation equation here. You can observe this is a perturbation equation, that is h power 1 psi n power 0 plus h naught h power 0 psi n power 1, which is equals to en power 1 psi n power 0 plus en power 0 psi n power 1. So here psi n power 0 is nothing but unperturbed state, isn't it? So this is unperturbed state. This is undisturbed state, so that we can write it as phi n. So we can write it as phi n, and here also we can write it as phi n, because this psi n power 0 is unperturbed state, whereas psi n power 1 is the first order perturbation, isn't it? So we need to find this term actually. We need to find this psi n power 1 term. Okay, we need to find this one. As this one is unperturbed state, we can write it as phi n, because we have considered as phi n as a unperturbed state in the Rayleigh-Ridge method. So here if you see, we have considered that phi 1, phi 2, phi 3, phi 4 and phi n up to phi n. These are what? Unperturbed state. That's why this psi n power 0 can be written as in terms of phi. So here that's why we are replacing with the phi n here, because it is psi n. So if you replace that, that is h power 1 phi n, that is plus h naught phi n power 1 is equals to en power 1 phi n, that is e power 0 phi n power 1. So again we can do that. We can write this equation in terms of ket, that is h power 1 phi n plus ket phi n plus h naught ket phi n power 1 plus e power 1 ket phi n plus e power 0 ket phi n power 1 psi n power 1. So we will multiply the whole equation from left with uh, ket phi m. So we will get this equation, that is inner product of, sorry, bra phi m h prime h power 1 phi n plus bra phi m h naught, that is phi n power 1 into ket psi n power 1, which is equals to en power 1. So en we have written outside, en power 1 is written outside the inner product of phi m and psi n plus en power 0 phi m psi n power 1. So if we observe here, this is inner product of different functions, isn't it? This is the inner product of different functions. This is in terms of phi, this is in terms of phi. At m is not equals to n, we know that. So m not equals to n, so that the value of this inner product will be equals to 0. This is orthogonal condition, isn't it? But here we cannot say that phi n power 1 is not equal to phi m. That is, psi n power 1 is not equals to phi m. That's why we will keep it as it is. And also, we need to find the psi n power 1, isn't it? So, we will keep this as it is. And here, h naught is what? H naught is Hermitian. In the earlier class itself, we have said H naught is Hermitian. So, we can write this as H naught psi n naught is equals to E n naught psi n naught, isn't it? So, this can be written as E n naught inner product of phi m and psi n power 1. So, we have written as it is the first term, and the second term we have written E m naught into phi m into psi n power 1, which is equals to, this is 0, the first term is 0, and the second term as it is we have written. And we have taken out, in the next step, we have taken out the E m naught to the other side, and we got the equation that is LHS equals to psi En power En power 0 inner product of phi m psi n power 1 minus En power 0 phi m psi n power 1. So, in the next step, we will take out the common. We will take out the common. Here, the common term is phi m psi n power 1. This is what? Phi m psi n power 1 is a common here. So, we can write this equation as, this is psi n power 1. So, this term is common here. So, in the next step, we can write this as En power 0 minus En power 0 into inner product of phi m into psi n power 1, isn't it? So, we can find inner product of phi m and psi n power 1 as uh, inner, that is bra phi m h prime h power 1 into h phi n by En naught minus Em naught, isn't it? So this equation is this equation is placed in or substituted in the equation which we have taken, that is this equation number 2, that is psi n power 1 is equals to I cap psi n power 1, that is after substitution we got this equation. So we have to substitute in this equation 3, that is inner product of phi m and psi n power 1 is having some value from the equation which we have found. We have to substitute in this equation so that we will get this equation, that is the second equation can be written as psi n power 1 is equals to summation over m naught equals to n inner product phi m at psi n power 1 uh, at phi m. So, as we know this value from the equation 3, so we will substitute in this equation. So, after substitution, we are getting the equation summation over m naught equals to n inner product phi m, sorry, bra phi m h power 1 phi n by en naught minus em naught into pet phi m. So, this is the equation 4. This is what? This is the first order correction to wave function. This is what? The first order correction to wave function. So, we can write overall the equation, that is equation 4 in the first is the first order correction to wave function, that is we can write in terms of like this m and n gets so summation over m naught equals to n, that is bra m h power 1 hidden by en naught minus em naught into m. This is the first order correction to energy, sorry, wave function, and the corrected wave function will be, so psi n is equals to, this is the corrected wave function, this is unperturbed wave function. Psi n naught is what? Unperturbed wave function here, unperturbed wave function, and we have the second term, which is what? This, which is the first order perturbation. This is what? Perturbation term, or first order perturbation to wave function. This is what? First order perturbation to wave function, that is psi is equals to psi n naught plus psi n1. So if you find a second order also, we can write plus psi n power 2. This is the corrected wave function. If you find psi n power 2 also. So this is about the first order correction to wave function. I hope you understood the class, and thank you for listening. Bye.